My whole computer's not being happy right now. There we go. So we should be starting at number 12 in your notes. Is that right? Or 11? Should be 11. Okay. So that's 11. Oh, and my thing is off. Wonderful. Let's fix that really quick, or that's going to drive me nuts. Come on. Doesn't want to do that either. Okay, so reactions between an acid and a base. If you've got Arrhenius's version, okay, Arrhenius's version, which we had an H plus and an OH minus go together, make water, then we'll get what we call, okay, fine. Then what we get is a salt. Oh, I just love technology. It sucks some days. Okay. Come on. Okay, we're going to do this again. Hopefully it goes up. Pause this. There we go. We get what is known as a salt, okay, and we get water. And this is when we have Arrhenius acid and base. They will always give us a salt and water. Now, sometimes the salt is neutral and sometimes it's not. So as we're looking at this, which one of these two would be considered my acid, which one my base? Okay, 2HCl would be acid, and then that leaves MgOH to be my base. So we've got an acid and a base yielding salt and water, and that only works when we're with Arrhenius. Okay, when we're with Bronsted-Lowry, we always get a charged system, where we get a conjugate acid and a conjugate base. But Arrhenius gives us a salt and water. Okay, we're going to be learning a technique today. It's called a titration. And in order to do a titration, you have to have either an acid or base that you know the concentration of, and then you have an acid or a base that you don't know the concentration of, and that's why you do a titration, to figure out the concentration, find out how strong it is. Okay. Sometimes we use what is called a pH meter to put in there. Sometimes we just do a simple titration, because if we've got our titration technique down very, very good, then it's very easy to do a quick titration and find the concentration fast. We are just, in general chemistry, going to be doing a quick titration. In other words, a basic titration without a pH meter. But if we had a pH meter, what would happen is, if I had a strong acid versus a strong base, I would titrate, and this would be 0 to 14. I would start around here with my titration because I've got a strong acid. And as I go along, I get to a point at which the acid and base are equal. Okay, or all my acid has been used up. Sorry, not equal, because that would be down here. All my acid has been used up, and now I'm just putting base into it. And then the titration curve goes basic. That is a strong acid, strong base curve. Okay. If I have a weak, so this is strong acid, strong base. If I have a, say, strong acid with a weak base, then my titration curve looks like this. I start down low again, but as I come over here, again, this is 0, this is 7, and this is 8. I come over here, it actually curves and comes over, and my equivalence point is not 7, but it's below 7. Okay, where this one, the point of, does anyone know what this point is called on a curve for math? This point right here is what's known as the inflection curve, or the inflection point. That's where the graph stops from going one way to going the other way. Okay, so we have one curve going to the other curve. So if we look at this, the inflection point on this one over here is below 7. So if a strong acid with a weak base, I get an inflection point below 7. Now, what happens if I do a weak acid with a strong base? Okay, again, we've got 0 to 14. And if I have a weak acid, I'm going to be up here to start the titration. And as I go, I'm actually going to be above the 7. Now we can do the titration backwards and say, okay, what if I start with a base and I get the acid? It's going to be basically the same thing. But what you want to remember is whatever's strong, if something else is weak, it's going to be on that side of the pH thing when we get our point of inflection. But I can go backwards like this and have a strong base titrated with a strong acid. It can go backwards, okay? So there's a lot of different titrations that you can set up and do. Now if I have a weak acid and a weak base together, that is known as a buffer, okay? We have several buffers in our system to keep our blood at a certain pH. If we break those buffers by, say, drinking too much alcohol or drinking too much water, believe it or not, we can break those buffers. And when we break those buffers, then if we add too much alcohol, base, or acid into our system, we can actually kill ourselves. Okay? All right, let's go on. So, equivalence point is when I've used up, that was a point of inflection. The titrant, this is point of inflection. I cannot spell. Okay? The titrant is what is being added from the burette. We put acid-base indicators in there when we don't have pH meters so that we can see where the end of the titration is. Because if we didn't have acid-base indicators in there, we could keep titrating forever and not know that we finished. Okay? So it would be like doing a race, running a race, but not having a finish line. Okay? Which would be really difficult because you never know when the race ended, right? So an acid-base indicator changes color depending on pH. Well, on those curves that I told you about earlier, we want an indicator that would change about the point of inflection, because we would want to know when that jump occurred. Okay? The difference between the equivalence point and the end point is this is where the indicator changed colors. So if we don't choose an indicator that changes about the equivalence point, then we've got a problem, because we want them to be about the same. Okay? Now we've got several different indicators. When you took your pH papers home, it basically had several different indicators on that pH paper, and they change color depending on what you put them in. Okay? We have liquid pH indicators that we put into solutions that will change colors. You can make your own at home. You can take red cabbage and boil it and save off the juice, and the juice will change colors depending on what you put it in. Same thing with grape juice, it will do the same thing. You can do that with X-Lax, it'll turn pink. There's a lot of different things that you can do at home to get indicators. All right, let's go on. I'm going to have you watch this. It's sort of a dry video, but it was really good as far as what is a titration, how do you do it, and what we're going to be doing next time. So hopefully we'll get this started. Start that again. Sorry, I have my thing on mute.
Titrant into an analyte solution in a titration until the endpoint of the reaction is reached. Used to swirl the flask while the left hand controls the stopcock from behind the burette. Rotate the stopcock with your thumb, pointer, and middle fingers. This allows better control for delivering partial drops. Check to see if the burette is clean by rinsing with water and noting any beads on the walls. Make sure the stopcock is closed. Bring the burette down below eye level. Use a funnel to add small portions of titrant for rinsing.
Titrant is your known solution, whatever you know. Okay.
Wet all areas of the burette with your titrant by rotating horizontally and drain out through the stopcock. Drain all rinses completely. Repeat this 3 times to ensure all contaminants are out. Fill the burette above the 0 mark with your titrant. Pour with the burette below eye level. Pour slowly so the burette does not overflow. Remove the funnel after filling. Check for bubbles in the burette, especially in the tip. Bubbles will cause significant errors in volume. To remove any bubbles, quickly move the stopcock back and forth. Move the burette 0 mark to eye level to avoid parallax and drain slowly to the 0 mark or below. Remove any hanging drops from the tip of the burette by touching it to a clean glass surface. Any drops are considered delivered volume. Record the initial volume by using a card with a dark line. This helps darken the meniscus curve for better reading. Read it to 2 decimal places. Add 2 to 3 drops of indicator to your analyte.
Analyte is the one you don't know.
It is wise to do a rough titration to determine the relative volume needed to reach the endpoint. Place the flask under the burette on a white background. The color change will be more noticeable. Adjust the burette so the tip is inside your flask to avoid loss of titrant. Add the titrant rapidly at first, with constant swirling. As the endpoint approaches, the color will be more persistent. Slow the drops down to 1 per second. Touch the tip to the sides of the flask and wash the sides down with water so that all titrant that has been delivered has reacted. Slowly open the stopcock and allow a partial drop to form. A partial drop just covers the tip of the burette. Touch the tip and rinse until the endpoint is reached. The endpoint is noted by a faint color that is persistent for at least 10 seconds, but not permanent. Obtain a final reading. The volume titrated is the difference between the initial and final reading. The concentration of your analyte can now be calculated. Let's review the steps. Make sure the burette is clean. Rinse 3 times with small portions of titrant. Fill the burette with titrant to above the 0 mark. Remove any bubbles. Drain to 0 or below. Take initial reading. Add indicator to analyte. Titrate quickly at first, then drop per second. Touch tip and wash side to flask. Add partial drops and wash sides until endpoint is reached. Take final reading. Calculate your concentration. Now you are ready to titrate.
Okay, so I told you it was a little bit of a dry video, but it went through the steps really well, I thought. So you got a little, the only thing they didn't do was we're going to be titrating or using a pipette to put our analyte solution in. You remember the analyte is the one that we don't know the concentration to. So we need to put an exact amount in of the analyte. We're going to be using 3 milliliters. We're going to be using a pipette with a bulb, my brain just left. Either a bulb, regular squish ball, or one that you actually can roll up. There's some of both back in the back. We're going to roll it up to 3 milliliters, or scoop it up to 3 milliliters, and then you'll put it into the flask. Now, adding distilled water to the flask does not change the amount of analyte I added. It doesn't change how much of the titrant that I need. So if I need to add some distilled water to it, it's not a big deal. Remember that the thing that I need to remember to add into here was my indicator, because if I don't know where the finish line is, right? Have no idea when to end. All right, let's go on a little bit. So now that I've done the titration, I need to be able to do the calculations. In this reaction here, if it is a 1-to-1, the number of hydrogens is equal to the number of hydroxides, I can use M1V1 equals M2V2. But if it's not, if I was to do a balanced equation and they are not the same like here, then I need to add in how many I've got for each of them. So, for instance, if this is going to be my hydrogen side, then how many hydrogens do I need for how many hydroxides? I need 1 hydrogen for every 2 hydroxides, right? So that I would just add that in to up here. So I times this side by 1 and this side by 2. Okay? So I can still use the same equation, but I just have to know the balanced equation of how much I have of each. So what is the molarity? So I'm looking for molarity of my acid. I don't know it. If I have a volume of 43.35 milliliters, and my molarity 2 is 0.32 molar, and my volume 2 is 25.9 milliliters. Now, my number of hydrogens that I need is 1 compared to the number of hydroxides that I need, which is 2. Can everybody see that? So the other way I can look at it is I need 1 of those, but in order to balance it, I need 2 times what I've been given over here. Okay? So then I just go in and plug in. So my molarity, I don't know. If I put a 1 in there, I could put a 1 in there. I don't have to, because it's just a 1. Times 43.3, I can write 5 milliliters, equals my molarity 2, 0.32 molar, times by my volume 2, 25.9 milliliters, times by 2, because I needed twice as much. Now personally, I like to simplify it down 1 time before I divide both sides, so I would go M1 equals 43.35 milliliters equals, and then I times this through on this side. Somebody do that? So you'll probably want to listen to this. Okay, so now, did somebody plug this through on this side? .576, so 8. Okay, and then I just divide both sides by 43.35, and I would get my molarity. And since, let's see, the molarity of there is 2, I only need to report to 2. So somebody got the molarity for me. It's going to be 0 point something. 0.38. And I put a capital M, and that would be my molarity of H2SO4. Okay? So if it's just 1-to-1, if there's one hydrogen to one hydroxide, I just throw it in M1V1 equals M2V2. Yes? Okay, did you take 16.58 divided by this number?
I got it for the first one.
For this one, you got a different number than this? Did you times it by 2? Okay, try it again, because this should be about 52. And then a third of 52 is about 16. If you need to just go check out.
Do I need to put it in parentheses?
No, you should be able to see what you're doing. 0.32, 2, and 2. Oh, because you're in scientific notation, so times it by 10. Yep. Okay. All right. Let's go on to the next part. Salt hydrolysis. So when I have a salt and it's added to water, some salts make things acidic and some salts make it basic. Okay? So if I have a metal oxide is going to add to water and give me hydroxides. And hydroxides are what? Base. These are bases. So depending on what hydroxide they give me depends on if it's a strong base, a really basic solution, or not. Okay? All right, so we need to be able to recognize our metal oxides. These are what are known as metal oxides. Okay, so it's just a metal with oxygen. Yes? Yes, those are the metal oxides. When I add them to water, then I get bases which are with a hydroxide. Okay? So we need to be able to recognize those. Well, if we take non-metal oxides, these are all non-metal oxides, then I'm going to get acids. And again, depending on what non-metal oxide I have, it could be a strong acid or it could be a weak acid. So if I take a salt or an oxide and I put it in water, I'm probably going to get an acid or a base. Okay? Yes? Acids have hydrogen. Yeah, hydrogen at the first. Okay? So non-metal oxides give us an acid. Metal oxides give us a base. All right, let's go watch this little video here.
Cause our rain to become acidified. Sulfuric acid arises from the burning of coal and oil, mainly in power stations, whereas nitric acid arises from the exhaust pipes of our motor vehicles. You will also see some of the effects acid rain has on our environment. Firstly, it's important to understand that rain is naturally slightly acidic. Whilst falling to the ground, the rain dissolves carbon dioxide from the atmosphere to form carbonic acid, a weak acid giving natural rain a pH of 6. It's when we burn fossil fuels that much stronger acids get into our rain to form acid rain with a pH as low as 3. When the pH changes from 6 to 3, what do you think the acidity increases by? 2 times? 3 times? 10 times? 1,000 times? Pause and think.
What do you think? 2? Okay.
Remember that each change of 1 in pH is a 10-fold change in acidity. So changing from 6 to 3 is 10 times 10 times 10, or 1,000 times more acidic. We'll consider sulfuric acid first. Plants need a little sulfur to grow. They obtain it from sulfates, for example potassium sulfate, found naturally in the soil. The sulfates are taken up by the plant's roots, and sulfur atoms become bonded to carbon atoms in the leaves' proteins. When plants die and eventually form coal and oil over millions of years, these sulfur atoms remain bonded to the carbon atoms. The sulfur content of coal and oil is usually between 1 and 4% by weight. What do you think is produced when fossil fuels containing sulfur are burnt? Pause the video whilst you think.
What do you think? Non-metal oxide or oxide?
When the coal is burnt, the sulfur and the carbon atoms join with oxygen from the
non-metal.
air and are released into the atmosphere as carbon
Non-metal
dioxide
oxide.
and sulfur dioxide. In the presence of sunlight, a photochemical reaction will take place where sulfur dioxide reacts with more oxygen to form sulfur trioxide. This dissolves in the rainwater, forming sulfuric acid. Let's now consider how nitric acid gets into the rain. In the high temperature conditions in the cylinders of our motor vehicles, a small amount of nitrogen and oxygen from the air can react. Remember that air taken in to combust the fuel is nearly 80% nitrogen. So exhaust gases from vehicles contain small but significant amounts of nitrogen oxides. Once the oxides of nitrogen are in the air, they react with more oxygen, just like we saw with sulfur dioxide, and dissolve in the rainwater to form nitric acid. If the rain falls on limestone soils which are alkaline, the acidity may be neutralized. However, if the rain lands on neutral or acid soils or on vegetation, then it can cause damage. So why is this acidity harmful to living things? Well, living things don't grow well in acid conditions, and it's easy to demonstrate this. Soak a slice of bread in vinegar and another in pure water, leave them open for a little while, and then leave them covered for a week. You will find that the bread soaked in vinegar has not gone moldy, whereas the other bread has. In fact, we use vinegar to preserve food in a process called pickling. This is the case because certain enzymes which are vital for growth are unable to function in acid conditions. The other main problem is in the soil. Whilst naturally occurring toxic metals such as aluminium are insoluble and therefore fairly harmless in neutral soil, they become soluble in acidic soil. They then get taken up by living things and take the place of essential metals such as zinc and iron. To add to this, the hydrogen ions in the acid rain will replace essential metal ions such as potassium, magnesium and calcium, which are normally held in the clay soil, causing these essential metals to be washed deep into the subsoil away from the roots of plants. So to summarize, normal rain is slightly acidic due to the dissolved carbon dioxide, but acid rain contains sulfuric and nitric acid, making the rain 1,000 times more acidic and dangerous for many living things. Sulfuric acid arises from the burning of fossil fuels containing sulfur. Nitric acid arises from the combustion of atmospheric oxygen and nitrogen in the high temperature conditions in the cylinders of petrol and diesel engines.
Okay, so I know you've talked about acid rain before at school, probably when you were in elementary school, right? But they didn't go that deep, right? They didn't tell you why. They just said it forms it. We don't have as much problem here because we have alkaline soil. So even though we get the crap from California coming in the winter and it really makes a mess, our alkaline soil sort of neutralizes it. All right, let's see. I wanted to go back to of course it went to a total minimalization here to this. Okay, so is everybody okay with, because we need to know a little bit about acid rain and stuff for our SAGE test at the end of the year. Everybody understand where we get them? Okay, so what comes from cars? Nice. No. It is integrative, so as you do better to get a better score, it gets harder. As you do horrible, it gets lower and you get a lower score. Okay, yes. HNO3, but what is given off by automobiles that makes that? nitrogen oxide. Nitrogen oxide. And remember, nitrogen oxide is a non-metal oxide that we just talked about, so you're going to get an acid when you add it with water. Okay, what comes off coals and fossil fuels? Sulfur. And when it combines, when we burn it, what happens? What does it become? Sulfur oxide. And when it's put in the air as sulfur oxide, it said something happened. What happened? Same thing that happened with the nitrogen oxide. More oxygens start combining with it, right? Because the UV. And then when it starts to rain, when we get water coming down, what happens? So we get hydrogen adding to it with some more oxygen, and that makes what? Sulfuric acid. Sulfuric acid. Why was acid rain acidic to start with? It combined with carbon dioxide and made carbonic acid, which is what is in our pops. Okay? And when we open up our pops, what happens? Releases the carbon dioxide and leaves us water. Carbonic acid is not very stable. Okay? It is a weak acid. Okay, so going forward, this is what we're going to do. We're talking a lot about strong acids and weak acids again. You picked up a salmon-colored or orange-colored POGL. I'd like you to get in your groups and work with your POGL. Do that first and then go to assignment 3. Now, I forgot to put one thing on here. We need to do the pre-lab and get it stamped for next time, so that when you come, you don't have to stay in here and do the pre-lab. You can go right into lab. And what I'm going to do is physically show you again when we get to lab how to do the titration again. And you're going to be doing it 3 times. So you get a good trial at it. Okay? All right. We'll come back together about 22-ish, maybe. I'm thinking as far as time goes, as far as what we need to do today, I'll probably put off correcting assignment 1 and 2 because of the time, and you need some time to get this done. Okay? So assignment 3 for next time. Okay? All right. Work hard.